Okay, it's 2:30. I'm going to pass these evaluation sheets out, and I need you to please bubble this in 67. Here you go. Yeah. Hey. Oh, how are you? Do you guys need more? They're going to be right here. Please grab one. Okay, so this is a live session, just so you know. You could be streaming this as well, as a reminder. This is the review for EGN 3310, section 4. I am your SI leader, Ivonne R. And I'm going to give you a few minutes to bubble this in real quick. I will be collecting at the end, so please give it to me at the end. Are you ready? Bubbled in 67? Okay. Okay, we are going to go over this problem first. Give you a few minutes to copy it. All right. So before we go through this problem, I'm going to explain how this session is going to run. So I am going to go through it, but I'm going to need your help on some of this, okay? So I need feedback, okay? All right, so looking at this problem, what would your initial step be? Label our reactions, right? Okay. So on this side, we know that this is going to be AX, going to have AY, and we also know there's going to be a moment there, right? Okay. So what else do we have here? Says supported by rocker at B and C. And we know that the reaction of the rocker is going to be like this, right? Just going up on BY and going up on CY. It also says there are hinges, pins at D and E. So that's kind of special, right? Pins are going to lead the problem. These are just steps that I use to remind myself, and that could help you also on the exam. I know that there's going to be 3 parts because we're going to have to break this apart. 1, 2, and 3. Okay? So how about we start with that? Let's break it apart. And let's label them. 1, 2, and 3. Okay, D. So if we're looking at here and we're breaking this apart, I'm going to decide that this is going to go like this. And a good way to help you understand why it does that is to look at page 305, example 6.17. Okay? So looking at this first section, what do we want to do? We could do sum of forces, right? Yes? Possibly? Maybe? Yeah? Okay. Sum of forces about dx. So we have ax plus dx is equal to 0. We could do sum of forces about y. Right? And we could also take a moment about A. And we have to include moment about A. And this distance, 6 meters. And that's negative, right, guys? Because it's going clockwise? Okay. So how about, well, I mean, if you look at this on its own, you can't really solve for anything, right? It leads you nowhere. So how about we go to part 2? So dy is going to go, dx, and dy is going to go up. We have a load. We have by. And we also have point E on there. Okay? We could do the same thing we were doing up here, right? So sum of forces about y. Oh, hold on. Sum of forces about x first. Get that out of the way. So dx plus dx, now y. Right? And I want you to hold off on the moment for a bit. So now section 3. Okay. So now you can have a good grasp of what's going on, right, guys? So section 3, cy, 6 meters. Here we could have.
Just a little bit for like signs, or scale, I should say, and then also just talk a little louder to the mic, just because the streaming isn't picking up very well.
Okay.
If you don't mind, thank you.
Sorry. Okay. Have to talk a little louder, apparently. Okay, so I forgot to put the distance on this. This is also 2 meters, and this is 2 meters. Don't forget that, please. So section 3, we have 6 meters, and we have E, right? So we have E going that way. We want it to go to the left. Okay? And our last part, we want EY to go like this. So we do the same thing that we were doing before. Sum of forces about the x. So negative EX is equal to 0. So now we have a piece of the puzzle. And now we do sum of forces about y. Okay? So it'd be EY plus CY is equal to 0. And now we could take a moment. Let's take a moment about E. So we could do CY times 6, and wait a second, what's going on? CY is equal to 0. That's the only moment we could have, right? So if we know CY is equal to 0, EY is equal to 0. Right? So this was the first one that really helped us. If we know EY is equal to 0 and EX is equal to 0, we know DX is equal to 0. Right? And now, because we know EY is equal to 0, and we're looking at this section, which would be a good point to take a moment. That's why I wanted you to hold off here. What do you think? I can wait, you guys. D? Awesome. Thank you. Take a moment about D. We have, let's see, it'd be negative 15, right? Times that distance. We have BY, which is positive. It's 4. And we also have EY over here. But EY is equal to 0, right? So we could solve for BY here. Do you guys see that? BY is equal to 7.5 kilonewtons. One, two, three. So now we have BY. If we have BY, looking at the sum of forces about y, we can know what dy is, right? If we were to just put it in, it's kind of simple, right? So it went from here to here. All right, let's go back up. We have dy. We can solve for ay. Be this, right? Okay. All right, going back here, we know dy. dy is going to help us find the moment about A, right? Moment of A is equal to 45 kilonewtons times that distance, meters. And this guy helps us out as well. So this is for the first one that we started with. We know this is 0, so AX has to equal to 0. Ooh. A little bit complicated, right? No. Okay, so a little extra thing you can use to check, because that's how statics works, is to use global to check. step 3. This is optional. The way I saw it, it was optional. So you could look at it as a whole, correct? Okay. And you could do some more forces about x. Ax is 0. Then you do sum of forces about y. Minus 15 plus by plus cy is equal to 0. Then we can also take a moment, have times 8, 6, 7, 8 away from a. By would be positive 10. And we have cy, which is also positive 12, 18. Okay? So I meant this as optional because you could start going about this and had already this done. And you could use by here. We had by and cy, and you could solve for ay. And then if you already had by and cy, you could have already figured this out. Okay? So any questions on that problem? You good? Okay. All right. Second problem. Gotta be this one. think we're ready. You guys ready? Okay. So the problem says, rod AB is fixed to a smooth collar D, which slides freely along the vertical guide. So it goes like that, right? It says, determine the internal normal force, shear force, and moment at point C, which is located just to the left of the 60-pound concentrated load. So I know it looks like it's right on it, but it's just a little bit to the left of that. All right, steps. What is our first step? Kind of like the last problem we did. What was our first step? Reactions. Perfect. Thank you. Label our reactions. All right, let's look at that smooth color D. So it allows you to go, looks like it allows you to go up and down, right? And our reactions, we know that our reactions are the ones that it doesn't allow, right? So we're going to have a reaction like this, going across the x-axis, and then we're going to have a moment, right? Okay? Let's see what else we have. We have an angle, and that's going to be problematic a little bit to understand it, but we're going to get through it. So let's put our second step is, I like to put loads, because then that way we'll deal with it right in the beginning. So loads here. What do we do for our load for this triangle? 1/2 base times height, right? And height's 15. Should give you 22.5, right? But we also have a load on the right, correct? Okay. 1/2, same thing, base times height. Okay. So step 3. This is why I like to look at it as a whole completely different step, is to deal with the angle. Okay. I'm going to try to draw this very nice for you so you can see it. That's our 30 degrees, right? That's our, that's point B, okay? So I know right off the bat, most of you guys will be like, okay, sine and cosine of 30 degrees, right? No, it was wrong. If you're looking for, and then you would give, okay, sine has to be y and cosine has to be x. No, okay. This is y. So if this was 30 degrees, this would be 60, right? If it was a perfectly 90-degree angle. Do you see that? Okay. So if this was a perfect 90-degree angle again, this has to be 30 as well, right? Okay. So then if that side's 30, this side's 30, right? So if I was going to draw this, it's be 30 degrees, correct? So now our sine is really on the x, and our cosine is really on the y, right? So we dealt with this. We now have everything. Now we got to figure it out. So let's look at it. Step 4. And it says determine the internal normal force at point C. So normal force NC, shear force, and moment at point C. All right, that's what we want at the end. So looking at this, how would you go about it? Would you solve it as a whole, or would you cut it? Because we want the shear at that point, right? Want to cut it? Does that make sense? Yeah? Okay, let's cut. And do we want to look at the right or the left? Right, okay. And we know this is going to be 11.25. We already figured it out. A length of 1.5. And we know that this, I'm going off of this, is b sine of 30. And this is going to be b cosine of 30. Okay, and we are going to incorporate the 60 pounds. So if we're cutting it if we're looking at the right side, our shear is going to look like this, right? Normal. And our moment's going to go up. Do you see that? Okay. So what do we want to do? What have we been doing this whole time? Summation of forces? Okay. Let's do y first. So we have negative 60. So then we do summation of forces of x. F and C, and we have B. Right? So we could take a moment, correct? And I want to take a moment about C. So moment about C, we are making it so that counterclockwise is positive, and we know that it's really negative when you cut it like this. So don't forget the negative. Okay, so how do we determine this distance? Do you remember a triangle? Huh? It's 1/3, exactly. So it'd be 1.5 divided by 3. Okay, so, and it is negative. And then we add, because this also has a moment, b cosine of 30 times your distance. It's equal to 0. Okay. So looking at this, we're kind of stuck at a dead end, right? We can't solve for anything. So what other option do we have? So if this was the problem on your exam, you're like, wait, okay, I did everything right. I'm missing something, so I could solve all of these. Well, you could. You would have VC. Yeah, you could solve it like that. But there's another way you could do it as well. That's a little bit like more basic that you would have started from the beginning. Huh? Okay, but as the whole thing, right? Right? You usually just look at a problem and you go, okay, I could do it at a global scale first. Correct? Okay. All right, so summation of forces about what? Let's see, I usually start with my y. We could do x. I'll show you what x is. It'd be dx, and then we said b was going that way, right? So it'd be negative. That again's not helping you, right? Go ahead. Yes. Thank you for reminding me. Okay, running out of room here. Okay, so summation of forces about the y as a whole. So what do we have? We have this load, right? So negative 22.5, that's taken from here. The 60 pounds, this load, and what else do we have? Awesome. And is it positive or negative? Positive, right? Awesome. Okay. So looking at this, you could solve for b, correct? Does that make things a little bit easier? All right, b should equal 108.25. So if you have b, you could solve for dx as well, correct? But our problem is asking us, determine the internal normal force, shear force, and moment at point C. So that kind of be extra, and you don't need it. So we have b. We have b, and we could solve for m of c, right? So this was key. M of c is going to equal 134.94 pounds per feet. We have b again. Thank gosh. It equals n of c. So n of c, you bring it over to the other side, it's positive, multiply it by that negative, it's going to be negative, right? And negative is telling us what? What does the negative tell us? So it tells us whether it goes up or down, correct? So this really is telling you, well, it's going to the right. Okay, so b again is really the key. So 1, 2, 3, 4. We can solve for v of c. Awesome. So did we complete the problem? Are we done with this problem? Yes, Brett? Yes, okay, thank you. All right, I'm gonna leave it on for a few seconds. Okay. Now we're gonna look at this problem, 757. Says draw the shear and bending moment diagrams for each of the two segments of the compound beam. You ready? Okay. So first step. What is our first step? What was that? Label reactions? Okay, perfect. Okay, we know that's a pin. CY, we have a roller. we have a roller right there in the middle. Okay. Step 2 is loads, correct? Yeah? Let me zoom in. Is that better? Yeah? Okay. Loads. Okay. So it looks like we only have one, correct? This big rectangle. 50 times 12, 14. Gives you 2100. Okay, something I kind of want to highlight that it tells us says draw the shear and bending moment diagrams for each of the 2 segments. So what does that tell us? We kind of want to take this in parts, correct? Okay, parts. We're going to have 2. I'm going to go ahead and label these. 1 and 2. Okay, so let's start by parts then. Let's look at the first part on its own. Up to by, it's 10 plus that 2, so 12. And this is going to be 2 feet. And we still have the same distance and the same load, so it's going to be that 2100. So summation of forces, correct? Okay. Force is about the x. Ax is equal to 0. Summation, well, let's put it down here. Summation force about y. We have ay minus the 2100 plus by. Okay? And we could also take a moment, right? And where do we want to take it? A. Awesome. Okay, so we have, is this positive or negative? It's negative. Awesome. 2100. And how far away is it? So, correct. So it'd be, this whole thing is 14. And it'd be half of that, correct? Okay. So then we have by, which is positive. I just gave it away. And how far is it away from A? 12. Perfect. Okay. So here we could solve for by. That is going to give you 1225 pounds. Okay, 1225. We have summation forces of y equation. Solve for ay, right? this is equal to 875. Oops. Okay. So we looked at the first section. Now we want to look at the second part, correct? So part 2. Let's try it. So we have CY, and on this one we put BY going up, correct? But on this segment, it's gonna go down. Do you see it? I have this load pushing down on it, correct? Okay. So BY is gonna go down. And then we have dy and dx. Don't forget your distances. Okay. So kind of like the same thing we did up here. We want to do summation of forces. Summation of forces about the x equals 0. Tells us that dx is equal to 0. Summation of forces about the y. Cy minus by plus dy is equal to 0. So we have by, correct? We solved up here? Okay. So that still doesn't allow us to solve for anything right here. But we do know by. So let's take a moment about what point? D, right? Could that help us? That could help us. So we know that this is equal to 1225. Take a moment about D. This is going in the positive direction. And it is 6 feet away. Okay? And then we have CY, which is going clockwise, so it's negative. And it is 8 feet away. This equation allows us to solve for CY. Gives you 918.75 pounds. So now we know CY. Now we can solve for dy. dy is equal to 306.25 pounds. Right? So we got our first steps done. We took this in 2 parts because I wanted it in 2 different segments. And now we're ready to do our shear moment diagram. So the first one I'm going to do is relating to this first part, the shear moment diagram. Okay? First is our shear, which is in pounds. Okay. So taking the solutions that we have from here, and we're doing shear, what point do we start our shear diagram? At A, correct. But what, so we have a reaction there, right? So we have to start at 875. So 875 is going to be up here. Okay. Okay, those words. Okay, so we know we have a reaction at By, correct? And it goes up 1225. But we want to determine what's going on right here. Right? This is, I drew this line to represent the point at B. So looking at our load, we know that the load's going to be equally distributed throughout this distance. It's going to be 12 feet, correct? Okay, so this is 12 feet. And if we multiply that 12 feet times that 150 pounds, it's going to give you 1,800. And that is the how much it's going to go down by, because it's a load that's going down throughout that distance. So if we subtract 875, 875 minus 1,800 gives you negative 925. And we know that that's the point that it ends up with, on point, up to point B. Do you see that? Make sure to label your points. Okay, so at point B, what's going to happen? It's going to go up, right? And we know it's going to go up by that amount. So at this point, it's going to be negative 925 plus 1225. And that's going to result in an ending at 300 up here. Okay? So this section right here, let me do it in green. That section is this, correct? That's that little bit we have left. So we're going to do the same thing we were doing up here. We have 150, and we multiply that by that distance. Times 2 is 300. Right? It's negative, because it's going down. It's a load that's going down. So at 300 minus the load that we have there is going to equal 0. And it's going to go down like this. Right? That is 2 feet. Okay, we just drew a shear. Now let's do moment. So something I always like to do that I've noticed after doing many of these problems is I just draw a line like this in between right there, because I know there's going to be a peak for your moment. Okay. So first part, we can take the area of these sections, right? That could tell us what our moment is. So we do, okay, half base, wait, what's our base? We don't know what that distance is, right? We know the whole distance is 12, but we don't know how long this is. I'm going to label that x. I'm going to label this as 12 minus x. So probably need more room. I'm going to put it over here on the right. I'm going to put similar triangles to find that distance. So we have x is equal to 12 minus x as that whole height, it's 875, is equal to this height, 925. Okay? So we just solved that. Solve for x, and we get 5.83 feet. And now we have our distance. We have our base. So going back over here for a moment, half base, we know is 5.83 times our height, 875. It's going to give you, there, let me write it. Half base times height. $22.52. Okay? So we know that it's going to go up to $22.52, starting from 0, because there's no moment at that end, right? Okay. So how do we figure out its shape? There's this awesome little neat circle, right? It says, please don't neglect infants, neglect dumb people instead. Remember that? So we look at this, we're like, okay, it's above this, which is positive. So it's positive and it's decreasing. And it's going to look like that. Positive, decreasing. It's going to look like that section of that circle. Here we have negative, and it's increasing. It's getting bigger. So it has to look like that other side. But we need to figure out at what point it lands first. So let's do part 2. Okay. So we're starting at that point, correct? We have to add that point to it. We're not starting at 0. Plus half of your base is going to be 12 minus that 5.83. Right? It's going to give you negative 300. And now we know our shape of this triangle. It's going to be negative increasing, and it's going to end at negative 300. So we draw it like this. Negative 300. And we have one more part to do, right? For the first segment. So here we have, same thing, right? Point before plus half of our base, which we know is 2, times our height, equals 0, right? Perfect. That's how we know we're right. And it is positive, and it's decreasing. Okay? more paper. All right, our second part, because we have two segments. Second part's a lot easier because we don't have a distributed load, right? Okay. Ooh, how's this gonna work? Okay. So, draw it like this. I draw it as if I had the actual segment. And then I know how many lines I have. Okay. So we know, what do I have right here? CY is 918.75. So what does that tell you for shear? This is CY, right? Equal to 918.75. Possibly that it starts there? Yes? Okay. 19.75. And, okay, so how's this gonna look like? Is it gonna go down or is it gonna go across? Across, right? Because there's no load that's making it go down. Okay? So we know at that point, I know it's kind of tiny, but that's where our BY is, right? 1225. So it's going to go down 1225 from that point, right? Yes. Okay. And that's going to give you at 0.306.25. It's 2 feet from BY. And let's look. So straight, or we're going to go up, or what do you think? Straight? Okay, because there's no load on that segment, right? Okay. And here is dy, 306.25. Wow. So we had negative 306.25, dy is going up 306.25, and we knew that our shear is correct. Okay, for a moment. Pounds per feet. Starts at 0. Okay. So for our moment, what do we do? What did we do before? Start at 0, perfect. And, sorry, what did you say? Oh, okay. Area, right? Is that the easiest way to go? Okay. So it's just going to be length, base times height, right? Base times our height. Right, that gives you 37.5. So, this is going to go just straight up, right? second part, we're gonna add the point before, right? And base times height, same thing, area. Okay, so be 6. This is 6 feet. That should give you 0. What? What do you need? Yes. That's for a shear, correct? Yeah, no, it's okay. So for shear, we're actually using the forces here, and then if we had a moment there, we would incorporate it, correct? Okay. So it's going to go down to 0, because that's how we know this is correct. Okay. So another way you could look at this is just a little extra if you wanted to. I know Mackie likes to do equations. You might like this way too, but I find the area much easier. Okay. So if we were arbitrarily looking at this, okay, let's just look at it. Let's draw it. AY. I'm going to label this distance as x. And this is going to be, we know it's 150. It'd be 150 times that distance x. Okay. And I know it have a shear, have a moment, had n. And I'm going to look at this. This whole segment is from 0 to 12 to B, because B caused this to go up. Okay, so we're going to look at everything up to point B. So x, this is the distance up to point B. Okay, so if we did summation of forces in the x, that wouldn't really help us now, would it? Don't need. Summation of forces in the y. So we have AY minus 150 times x, and we have our shear. Okay. And we could take a moment as well about that moment. So be the moment plus 150 x, and we know that this is going to be in midpoint, right? So that's the distance away from this moment. And then we have AY, which is negative, right? Yep. So here we have to have AY, correct? And we already figured that out. AY is 875. So we have AY, 875, 875. And we could solve for a shear equation. V is equal to 875 minus 150x. And we could solve for a moment as well. Negative, positive, minus 150x squared divided by 2. So these equations tell you, let's look at our shear. The behavior of, like if you're going to plug in point 12 up to 12, say plug in 12, it should give you this point, right? So somebody plug in 12 for me. What do you get? Do you get negative 925? Okay. Tells you this point. So our equation is correct. That's another way to look at it. And you would do the same way I did right here for this section and for these if you want to. But you wouldn't really need them. Okay? Good? All right. Do you need this anymore? No? Okay. Okay. So let's go ahead and look at this one. All right, let's take a step at this problem. Zoom in a little. All right, so steps, right? I like steps. Says locate the centroid x bar of the area. So what is our centroid for x equation? So just this integral, right? Hopefully Mackie will give you the equations. Okay. So this problem is not that hard. You just need to figure out what our dA is, right? Okay, so we're taking dx, right? These slices, right? So this is more like a math equation, right? So it's always going to be, this is my y1, y2, or your top, and your bottom. For this problem, it's going to be y1 minus y2 dx. So integral of what are boundaries? 0 to 1, perfect. So y1, x 2/3 minus y2, x 3/2 dx, right? So it'd be x 3/5, 5/3 minus 2/5 x 5/2. Integrated from 0 to 1. Because you're taking these dx slices and you're going from, you want this centroid, this is your x. You want the one that it's in between those, correct? You don't want to go off somewhere else. You want it in between these two lines. Okay? So that should give you 3/5 minus 2/5 is 1/5 meters squared. So now we have dA. Sorry, we have the integral. Well, we have dA, and now we have the integral as well. So look at our big equation. And we got to do this integral, right? We just figured this integral out. So we have to integrate from what to what? What are boundaries? 0 to 1, perfect. X times our dA, which is this, over the integral of dA, which we just figured out was this. Okay? So now we do that. Be like 5. And we know y1 is x 2/3 minus y2 x 3/2 dx. Correct? 5 equals 0 to 1. Thirds. And now we're doing the whole thing. 3/8 thirds minus 2/7 x 7/2 from 0 to 1. end up with 25 over 26 meters. Okay? So 929 says locate the centroid y bar of the area. It was 928. 929. Y bar. So our equation is similar to this. So you don't, if you forget, and you just remember one equation, remember it's the same thing. But with a y. Okay, so we have our dA, correct? Which we already figured out. It's going to be y1 minus y2, or our x 2/3 minus x 3/2. Okay, so there's a trick with this y, and I'm going to draw this here. We're still taking dx slices. But what do you notice about, let's see, we're going x. What do you notice about the y? It's a bit different, right? We're going to have to treat it differently. So whenever you have, so this is the general centroid, right? And it looks like each time it's going to be at a half. Okay? So what I like to remember, to not forget whenever I have a problem like this, our YC, this is that y, is this. It's going to be y2 plus y1 minus y2 halved, because you're going halfway. So this simplifies to half of y1 plus y2. So you're going y2, and then you want that point that is halfway of those two lines. Okay? So we're solving for this. We know we're integrating from, where are we integrating from, guys? For y? You know? 0 to 1? Okay, good. So our y is now this. Half of y1 plus y2. And our dA, x 2/3 minus x 3/2 dx over the integral over dA. And we know, since we're integrating 0 to 1, which we already did up here, it's going to be 1/5. So I'm going to rewrite this. 5 halves are y1 x 2/3 plus our y2 x 3 halves x 2/3 minus x 3 halves dx. And that gets to be, once you finally integrate it and just solved it out, you know, when you multiply, you add, you're going to get this number. Correct? Does this help you? Do you have any questions? Go ahead. You could flip it, yeah. It's just an equation. It's just the way I was looking at it. Yes? I'd have to, because I mean, you know, statics varies all the time. But for these, when you have top and a bottom, if it looks like this, I'd say go with this. Okay? But don't word me on that. But this makes sense though, because you're at halves. And I have seen other problems that you've had, you half it as well. Okay? Any more? Okay. Do you need this up for any more time? No? Yes. Over 56? Oh, shoot. Thank you. Is it for each one? Okay. What do you speak of? Just notice. Okay. All right. Sorry, guys. Okay. Good. We're good. Oh. Ooh, this one's fun. You guys love this one. let's look at this problem. It says locate the centroid y bar of the bulb T cross section. Okay, so what I like to do, and I suggest you do, you've probably noticed already, is to redraw this, right? And it's 3D, I want to look at it as in 2D. And I'm going to look at it as if it was just simple shapes. And this is going to be from the bottom. Okay? So we're going to draw, don't forget to put the lengths, 225 millimeters, 25 millimeters. This is 75. $75. 400. This is 50. And our last one, 100. Okay. So we know each of these, it's going to have a centroid, right? Okay. So step 2 is make a box. This is how I like to organize myself. It might help you as well. Okay. I'm going to move this a bit. Okay. So I'm going to make this really cool box. It's going to help you. I'm going to number these simple shapes. We're going to have 4. That rectangle, this rectangle, the 2 triangles, and the bottom rectangle. So for shape 1, it's going to have a row. Here we're going to have, okay, shape 2, shape 3, four, can't see it. Okay. So the reason I'm making this box is because we know that the equation for this centroid is going to be this, right? Okay. So I like to put this in parts. I like to have area as a whole separate line. And I'm going to need my summation of area, right, at the end, so we could put it for here. Okay, so the area of our first part is going to be 450 times that 50, correct? So the whole length, base times that height. So the area of our second object is going to be 75 times that whole length. And just so you can see a little bit better, it's this whole length. So 475. Then we take half of, wait, we don't know our base, right? But we do know this length. And we do know that the section in between is 75. So what I like to do is what I recommend to do as well, so that you don't do extra work, is to recognize that your base is going to be this base, right, minus that 75. So it's that 300 minus that 75. It's 225. So you're already counting both the triangles. Half base times height. For both. And we have our last area, which is the 300 times 100. Okay? So we could calculate, we would need to calculate all these, but I'm going to leave it like that. Then I'm going to determine where my y bar is from the bottom for each of these. Right, so where our y centroid is for each of these. Okay, so the first one, it's half of that 50, right? So 50 divided by 2 plus that whole distance. So we have this section right here, and now we need all that distance to the bottom. Right? So it's 575 is 600. So the second one, we're going to have to half this as well. So 475, because we know that whole length is 475, we need half of that. Plus that 100. That gives you 337.5. Okay? So now we need our triangle. So let's look at our triangle. If we're going, let me draw a triangle separately. We need this distance, right? Right? So if we're going to this, it'd be a third. Because if we're going from here, if we're going to this side, it'd be 2/3. But we need the distance. We need that little section right there, so we can add it to that 100. So it'd be 75 divided by 3 plus 100 equals 125. And this, we know we just divide by 2. Okay? All right. So our third column is going to be y bar times a. Sorry, y squiggly. So you can tell what we do now, right? We multiply this value times this value. So whatever 450 is times 50 times 600 is going to give you this big value. Same thing we do over here. 75 times 475 times 337.5 is going to give you, well, that's a big number. Now we can close our box. Now we do this side. And now we do finish with this one. So it'd be 100 times 50. It's going to give you 2, 3. And now we have all these values. We can just add them straight across. So that I get our summation of y, a. Squiggly. 48, 0, 7, 8, 125. And summation of areas is going to give you 96,562.5. All right, so now we can figure this out, right? We have the 2 parts for this. So our centroid is going to be this value divided by this value. It's going to give you 290.78 millimeters, or round it up. So does the box method help you? Helps you organize, right? And remember, you can choose whether you want to have from the top or from the bottom. It's up to you. Any questions for this one? Go ahead. Yeah, what do you get? For number what? For the 4th? What value? This one or this one? .05. Okay, hold on. So am I getting the final value wrong? Uh, are you okay? I don't think so. Hold on. I'm not sure. Come up to me after. I don't understand what you're asking me. These are the values that you should get. All right, let's do one more problem, and then that's all the time we have. Okay? Oh, okay, I see what you're saying. All right, for this one, yes, you're right. No. I just got dyslexic. This is a value. That's what you're saying, right? Okay, sorry. Yeah, I had it right here. I was just looking at the bottom one, unfortunately. Okay, so this is the answer. You're going to end up with this regardless, okay? Okay, let's start this one because I want to at least get through this one to help you guys out. Okay, so 1048. Steps. So our first step is going to be, says determine the moment of inertia of the area about the x-axis. So we have an equation for that, correct? Okay, so you look up the equation. And it'd be this one. And our second step would be, so I like to look at this as I'm taking away these parts, because then that makes things much easier, right? We're calculating the moment of inertia of the area, and if we took it as a big rectangle minus this triangle minus a circle, we'd end up with the right value. So our second step is find equations needed for each shape and x. Right? So each of these shapes are going to have their own equation for x. For a rectangle, it's going to be 112 base times height cubed. Triangle for x is going to be 1 over 36 base times height cubed. And for our circle, it's going to be 1/4 pi r to the 4th. Okay. Our third step, or something that can help you remember, is to know that for this dy, I like to think of it as from x-axis, and for dx, from y-axis. Okay? So, big rectangle goes first. 112. Its whole distance is 10. Our base is 6, right? And our height is 10. Cubed. I'm following this, okay? Plus area. So our area, you can just take it from this. So 6 times 10. And now dy squared. So like I said before, it was from x-axis. So it'd be half of 10, right? Squared. Do you see that? And that is for our big rectangle. And now we're subtracting our triangle. So now we're looking at our triangle for x. 1 over 36 base and our height cubed plus half, because now we need the area of the triangle. Half base times height. And now we need dy squared. So a dy squared. Maybe write that here. See it. Dy. So let's look at this triangle. We're coming from this side, right? So it's going to be 2/3 of that 6 plus 4 squared. So we have this distance, and now we need 4, because we want it from the x. Now we're subtracting the circle, okay? So our circle is going to be 1/4 pi times the radius, which is 2, it's given, 1/4, plus the area of a circle, pi r squared. Pi, radius is 4, squared. And now we need distance from y. So here, it's giving to us, right? It's 4. 4 squared. Okay, so we're going to have to, the only part that you actually maybe mess up is adding these and subtracting it. Trust me, that's the only part. And then you'd have times 10 to the 3rd inches to the what? What unit is this? To the 4th, right? Okay. And that's the moment inertia of the area about the x-axis. So for y, I know we only have a minute left. So let me set this up for you. y, you would do the same steps that we did up here, right? So we'd find out our equation. Iy is equal to Iyr plus a dx squared. Remember this. And 2. Find equations needed for each shape in y. So we're literally doing the same thing. But now we're doing it for y. So Iy for a rectangle is 1/12 height base cubed. For this rectangle, you're going to see it's going to be 1/3. And we are out of time. That tells me I'm out of time. But we would finish with, we would do the same thing across. But we have to keep in mind that we're taking it from a distance. The x is from our y-axis. So your distances are going to be from this axis. Okay? And that sums up today's review session. Thank you for coming. Please, the handouts that I gave out, if you didn't have one, fill it out and give it to me. Okay? Thank you guys.